This video contains notes and solutions to the book problems from section 10.3. This is about series and in particular infinite series, infinite series. The difference between a sequence and a series is that the series is a sum of numbers. So a series we could define like this. It's the sum from n equals 1 to, let's say some number k, however far it's going to go, of these terms a to the n. In other words, it's a1 plus a2 plus a3 plus dot 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 all the way up to the kth one. That would be a series. And sigma notation works well for that, of course, because that's a sum, right? An infinite series is exactly what you would guess, that the sum from n equals 1 to infinity. That does not necessarily have to be a 1. You could start somewhere else. Sometimes we start at 0, if that's convenient for us, of a sub n. A sub n is just what the term is, so that could be some expression here, right? Like our general term from the sequence problems in the last section. So this would be a1 plus a2 plus dot dot dot. Now, how the heck, you might be thinking to yourself, how the heck could an infinite sum of things add up to a finite number? But we already know the answer to that question. We've already seen, you've seen infinite series before. And there are some types of series, one type in particular, which is called a geometric series, an infinite geometric series. And what does that mean? The geometric series means that the to get from one term to the next, you multiply by the same number. So that would be, we have some first term, and then the second term would be the first term times some common ratio between the terms, and then that's a multiplication, not a dot on that, that's a 1. And then this would be a1 times, if we multiply by r again, and this would be the first term times r again. So to get from one term to the next, you just keep multiplying by that same common r. And if you want, you could say, oh, well, we could write that in sigma notation, right? The sum from n equals 1 to infinity of a sub 1 times r to the, and you see this is r to the, for the second term it's r to the first, and the third term it's r to the second, it's just r to the n minus 1. You could write it like that, in sigma notation, if you wanted to. And you know, for example, that there's the infinite geometric series, 1/2 plus 1/4 plus 1/8 plus 1/16. It's a geometric because I multiply by 1/2 each time to get from one term to the next. Dot dot dot. And there's a nice geometric, in fact, way of understanding how that all adds up to something. You could say, well, here's, if this is a square, there's the area of the first triangle, half the square, that, and then this half of that half would be a quarter, and then you can keep cutting it in half, and you can keep doing that forever and forever. And I hope that phone doesn't keep ringing forever. Oh, great. Unlike the phone, which stopped ringing, this will keep on going on forever. And you can see it adds up to the whole square if you let it go on for infinity. So the area is 1. So this whole infinite geometric series is 1. Right? It sums to 1. Now, in general, there's a couple things we might observe. There is a formula for the sum of an infinite geometric series, and I'm just going to take you through. You don't need to know how to prove this, but I don't want to just drop the formula on you. So, proof of sum of infinite geometric series. So we'll start like this. So here's my infinite geometric series. I'm going to use it in this form. So let's say the sum is S. I don't know what S is equal to. I'd like to find a formula for that. And S is equal to A1 plus A1 times R plus A1 times R squared plus A1 times R cubed, and so on, off to infinity. Now I'm going to take that series and I'm going to multiply it by R on both sides of the equation. So if this is true, then R times S is equal to this here. I can multiply this side of the equation by R and then also multiply this side of the equation by R. When I multiply R times this, I get A1 times R. When I multiply R times this one, I'm staggering them so I have the like terms lined up. But I think it's pretty clear that if you multiply the whole thing by R and then dot dot dot, you get the same thing here, right? And then I'm going to subtract here. So here I have S minus R times S is equal to, and here all of these cancel out except for the very first one. And if you're thinking to yourself, wait a minute, there'd be one extra one here. No, there isn't, because they're going off to infinity. There is no extra one. And that means that solving for S here, factoring out that the sum is equal to the first term, A sub 1 over 1 minus R. I'm going to write that big over here. The sum of an infinite geometric series is the first term over 1 minus the common multiplier. But there's a big caveat that goes with this. This does not always work. You can't just do this with any geometric series. What has to be true about the R? The R has to be in between -1 and 1. Which is the same as saying that the absolute value of your ratio, your multiplier, has to be less than 1. I think pretty obviously if it's not, then you don't get a finite sum. If, for example, your R was 2 and your terms keep doubling and your terms keep getting bigger and bigger and bigger, you can't add up to some finite sum. But if R is anything in between -1 and 1, it works. If it's -1, it doesn't work. If it's 1, it doesn't work. But in between -1 and 1, it does work. There's one other series that we need to talk about here in this section. And if you read the book, they make the claim that it is the most important, or one of the most important, divergent series. I would say maybe it is even the most important. It is called the Harmonic Series. If you're interested in knowing more about why it's called that, and if that has anything to do with music or whatever, I can talk to you about that sometime. Right. It's called the Harmonic Series. And the Harmonic Series is this series. It's the sum, n equals 1 to infinity, 1 over n. And that looks like 1 plus 1/2 plus 1/3 plus 1/4, etc., etc. And I'm actually going to write out some more terms here, and you might wonder why I'm doing it in this weird way here, but I'll explain in a minute. I'm just kind of including some selected terms and leaving out other ones. And why am I choosing these ones? Geez, if you could figure that out before I tell you, I'll give you a sticker. Alright, so anyway, it goes on and on and on forever, right? Just 1 over the next number, 1 over 1, 1 over 2, plus 1 over 3, plus 1 over 4, etc. We're going to try to make an argument that this series diverges. And I'm going to do it like this. The first term, is just equal to 1. The second term is just equal to a half. Now, the next thing I'm going to do is I'm going to look at these two terms here. I have two terms here. The last one is 1/4, and there are two of them. And I think you would agree that terms in this are getting smaller. There's no exception to that. They just keep getting smaller, 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 smaller. And so that means here, if you go backwards, they get bigger. So here I have 1/4 plus another term that's at least a little bit bigger than 1/4. In other words, these two have to be bigger than 2/4, because this one is 1/4 and this one comes before it in the list, so it must be bigger than 1/4. So whatever I have here must be at least a little bit bigger than 1/2, right? Bigger than 2/4. The next four terms in the series, well, the last one's 1/8, and then I have three other terms, the 5, 6, 7, and 8. I have three other terms, rather, the 5, 6, 7, right? Those are all at least a little bit bigger. They're all a little bit bigger than 1/8, at least. I think that's fair to say, right? They're all at least a little bit bigger than 1/8. In fact, 1/5 is quite a bit bigger. So that means I have four terms that are at least either equal to or bigger than 4/8, or 1/8, so I have a total of 4/8 or a little bit more. So all of those terms together must add up to at least 1/2, right? Because it's at least 4/8. Now the next 8 terms here are either equal to 1/16, the last one, or bigger than 1/16. So all of them together have to be at least 8/16, but of course that's 1/2. And then the next 16 terms are all either equal to 1/32 or greater than 1/32. So the 16 of those must be greater than 16/32 or 1/2. And you can see, and so on, and so on, and so on. So I can keep going on forever. This series goes on forever. So there's no end to this process. And if I can keep finding bits that are equal to or greater than 1/2, then this must diverge, because although it's going to take me a long time to get there, I can get to any number I want. So that's interesting. And that means that the harmonic series diverges. Why is this series so important? Well, we'll talk about that some more soon. But and I think maybe we've hinted on this before, or hinted at this before, that the harmonic series is kind of like a line in the sand between series that do converge and series that don't converge. And we'll talk about that more, I think, as soon as the next section. But for now, to sort of sum up the notes part of this, basically all we know at this point is two things. If you have a geometric series, a series in which you get to the next term by multiplying by the same thing over and over again, that we have a formula for that sum. If the multiplier is in between -1 and 1, then you can use the geometric series sum formula. We know that, and we also know that the harmonic series diverges. And that's all we know, right? That's all we know about series right now. So if you haven't tried the homework yet, then this would be the time to stop this video and try the homework. It's pretty quick. It's only 10 problems, and they're not that hard. Let me just give you some extra encouragement for the last couple of problems, which I think is, what are the last couple? 26 and 27, I think, right? Just give you some extra encouragement on those, to really try those and think about them and play with those problems a little bit before you just say, I have no idea what the heck this is, and look at the video, okay? You can do those problems. Those are the kind of problems that involve a little bit of playing around with them to try to figure out what's going on before you give up, Okay? That is super, super, super important that you do that. If you end up playing with it for a while and don't get the right answer, that's okay. You'll be much better off for having messed around with it a little bit. So get your hands dirty and try those problems before you give up. Okay? So here are the problems. 3 through 6, these are all geometric series. Some of them might be a little bit harder to recognize as such. And it's never a bad idea to go ahead and write out the first few terms if you're not sure exactly what's going on. So let's see. When I plug in 1, that's the 0 power. Anything to the 0 power is 1. When I plug in 2, that's to the first power, so I get minus 3/4. When I plug in 3, I get negative 3/4 squared, and then I think I can see from here what's going on. So this is a geometric series. The first term is 1, and every time I'm multiplying by negative 3/4. This is in between negative 1 and 1, so the sum of this series is the first term over 1 minus the multiplier. Don't be a fool and make a sign mistake there. Sorry, I didn't mean to insult you if you did. But that happens a lot in this formula, so be aware, right? That's going to turn into plus if you have a negative multiplier. So 1 plus 3/4 is 7/4, and that flipped over is 4/7. So it converges to 4/7. Number 4. We have a series from k equals 1 to infinity. 2/3 to the k plus 2. So obviously 2/3 is my multiplier. As this ticks up, I keep multiplying by another 2/3. The first term, when I plug 1 into this, it's 2/3 to the third power. So that would be 8 over 27, right? And then the next term would be that to the fourth power, so that would be 16 over 81, and then 32 over 243, and so on. So my first term is 8 over 27, and my multiplier is 2/3. First term, 1 minus the multiplier, so that's 8 over 27 divided by 1/3, which is the same as multiplying by 3 over 1, so that's equal to 8/9. Yeah, there's going to be fractions, so there you go. 5, we have the sum from k is equal to 1 to infinity, negative 1 to the k minus 1 times 7 over 6 to the k minus 1. This is a sign flipper, right? So let's write out the first couple of terms here, see what's going on. So when I plug in 1 here, k minus 1, that's 0, negative 1 to the 0 is 1, so I'll have a positive term. And I have 7 over 6 to the 1 minus 1, so the first term is 7, right? 7 over 6 to the 0. And this is a sign flipper, so the next term is going to be minus, and then I have 7 over 6 to the 1, and then the next term will be positive. Notice that the 7's not part of the multiplier, right? It's just 7. There's no k up here. And then 6 squared, and so on. So it looks like my first term is 7, and my multiplier is negative 1/6. If the signs are flipping, it means you got a negative multiplier, right? So that means the sum, I've got an r that is in fact between negative 1 and 1, so first term over 1 minus the multiplier, that's equal to 7 divided by 7/6, which is the same as times 6/7, and that's equal to 6. Converges to 6. And last one from this group, we have the sum from k equals 1 to infinity, -3/2 to the k plus 1. I'm just going to write out the first two terms. Plug in 1, that becomes the power is 2, so this negative squared to positive, and then when I raise it to the third power, I'm going to get minus 27/8, etc. So the first term is 9/4, and the multiplier is -3/2. Uh-oh, I hope you're paying attention. The multiplier is not between -1 and 1, so this diverges. You can plug that into the formula and you can get a number, but it does not make any sense. If the terms are getting bigger and bigger, as they will if you multiply by 3/2 every time, whether they alternate or not, if they're getting bigger and bigger, you cannot converge to a finite sum. So please watch out for that. Number 11. We have the sum from k equals 3 to infinity, or 1 over k minus 2. And you plug in the 3 and you realize very quickly, hey, this is just the harmonic series. That diverges. If you ever need to make a case, you can say it diverges because this is the harmonic series. That's a fact that you are expected to know. The harmonic series diverges. You don't have to say more than that. Why does it diverge? Diverge, rather? Because it's the harmonic series, and everybody knows the harmonic series diverges. I mean, seriously, right? So the next one, k equals 5 to infinity of e over pi to the k minus 1. Not the first couple of terms. First term, that's going to be a 4, so that'll be e to the 4th over pi to the 4th. And then the next term will be e to the 5th over pi to the 5th, etc. So the first term is e to the 4th over pi to the 4th. And then the multiplier, every time we multiply by another e on top and another pi on the bottom. So e over pi, that's a pretty funky ratio, but it is less than 1, right? E is 2.7-ish and this is 3.14-ish, so we can use our formula. So first term over 1 minus the multiplier. And I don't know, I guess you could leave it like that if you wanted to clean, if that's offensive to you to have that complex fraction, if you feel like that's a fraction in fraction in fraction, then you could multiply the top and the bottom by pi to get rid of this denominator. So let's do that and see what we can do to clean this up. It does offend my sensibility, by the way. So e to the 4th over multiply the top by pi because pi cubed on the bottom, and then if I multiply by pi on the bottom, I get pi minus e, and then dividing by pi minus e is the same as multiplying by the reciprocal of pi minus e, so that's e to the 4th over, and distributing pi to the 4th minus e pi cubed. I think that's a better way to write it. Right there. But it doesn't really matter. That's not the point of the problem. Number 13, got the sum from k equals 1 to infinity of 4 to the k plus 2 over 7 to the k minus 1. First couple of terms, if I plug 1 in, I get 4 cubed. I'm just going to write it like that. Over on the bottom, I get 1, right? Next term would be 4 to the 4th on top over 7, and you can see what's going on there. So this is geometric. The first term is 4 to the 3rd, and the multiplier is 4 over 7. Every time I get multiplied by another 4 and another 7. So 4/7. That is in between -1 and 1. So the sum is the first term over 1 minus the multiplier. That's 64 divided by 3/4, which is the same as multiplying by 7/3, which is, let's see, 60 times 420, 448 over 3. Oh, that was a really silly way to do that, wasn't it? I should have divided this first, because 64 divided by 3 is... Oh, no, it doesn't go into that, does it? Never mind. Just kidding. It's 448 over 3. Number 14. Let's see. We've got the sum, and k equals 1 to infinity of 5 to the 3k times 7 to the 1 minus k. So let's see if we write out a couple terms here, what we got. So the first one's going to be 5 to the 3rd over, when k is 1 here, that's just 1. And, sorry, I guess I'm writing it as if you're wondering why I wrote a fraction bar there, I'm anticipating that these are going to get negative, so, and that's going to be easier for us to understand that way. So when I plug in 2, I get 5 to the 6th plus, oops, sorry, on the bottom when I plug in 2 here, 7 to the -1, which is the same as 7 to the 1 on the bottom. When I plug in 3, I get 5 to the 9th, and then here I get 7 to the, when this is 3, 7 to the -2. So that should be plenty to see what's going on here. First term is 125, 5 to the 3rd, and my multiplier is 125 over 7. And that is quite a bit bigger than 1, so this diverges. You got to pay attention, right? You can't go through these problems without doing that, pausing to check and make sure that you got a good R that you can use your formula. In this case, we could not use the formula. All right, the last two problems, by far the best problems, are 26 and 27. Number 26, use geometric series to show that the sum from k equals 0 to infinity, -1 to the k times x to the k is equal to 1 over 1 plus x if x is in between -1 and 1. All right, well, let's look at this and write out some terms here. If I plug 0 into this, I get 1, right? -1 to the 0, x to the 0. If I plug 1 into this, I get -x. If I plug 2 into this, I get plus x squared, and so on. Well, that's a geometric series, right? With a first term of 1, and every time here I'm multiplying by -x, right? So the formula for the sum of an infinite geometric series, ... is the first term, 1, over 1 minus the multiplier. But that's true only if the multiplier if negative x is in between 1 and negative 1. And that's the same as this. That's the same as that. And of course this is the same as that. So we did it. It's just a matter of understanding that like a geometric series. That's part A. Part B, if you didn't get this one, you need to pause the video now and try B and C on your own. And also try number 27. Okay? Because they're the same as this. So stop watching the video. Try to do the rest of those now if you were stuck. Okay, you're back. So now you're just checking your answers because you did these, right? And we got, they want us to show that this is equal to 1 over 4 minus x if 2 is less than x is less than 4, if x is in between 2 and 4. All right, well, let's write out the first few terms. First term, when I plug 0 in here, would be 1. The next term would be x minus 3 to the first power, and then x minus 3 to the second power, and so on. Well, that's an infinite geometric series where the first term is 1 and the multiplier is x minus 3. Right? So the sum of an infinite geometric series is 1 over 1 minus the multiplier if the multiplier, the absolute value of the multiplier, is less than 1. Now this simplifies to be plus, that simplifies to 1 over 4 minus x, and this simplifies to, that's what that means, absolute value less than something means it's in between the positive and negative version of that. Add 3, so that means this, and that's what we're trying to show. No sweat. And then the last one, not that you need to show me at this point because you've mastered this, negative 1 to the k, so the signs are going to flip, x to the 2k. I'm going to show that that's equal to 1 over 1 plus x squared if the x is between negative 1 and 1. Alright, so let's see if we can make sense of that. First few terms of this, plug in 0, you get 1. Plug in 1, you get negative x squared. Plug in 2, you get positive x to the 4th. And so on. That's an infinite geometric series with a first term of 1 and a multiplier of negative x squared. So the sum would be the first term over 1 minus the multiplier if the multiplier, the absolute value of that is less than 1. So let's see, that'd be x squared has to be less than 1, and for x squared to be less than 1, x can be anything between negative 1 and 1, and this, of course, turns into that. And if you're thinking, hey, that's the derivative of the tangent inverse function. Well, that, you're right, and that foreshadows a connection that we will make later down the road, but not until section, I don't know, 10.8 maybe, something like that. But good on you if you thought that might be a thing. And then 27. In each part, find all the values of x for which the series converges and find the sum of the series for those values. So this is the same thing that we just did, right? If our series is x minus x cubed plus x to the 5th, etc., then the first term is x and the multiplier is negative x squared. So the sum would be the first term over 1 minus the multiplier, and that would be true so long as the multiplier is in between negative 1 and 1, and for that x squared we just did that. means that. So those are the x values, and it would converge to x over 1 plus x squared, but only for x values in between -1 and 1. In B, our series looks like 1 over x squared plus 2 over x cubed plus 4 over x to the 4th, dot, dot, dot. So the first term is 1 over x squared, and the multiplier is, looks like we're multiplying on the top by 2 and on the bottom by x. So the sum would be the first term, which is 1 over x squared, over 1 minus the multiplier. And that's going to converge so long as the multiplier is in between 1 and -1. Right? So, don't worry, it's not my phone. So I'm going to clean these up a little. I'm going to clean that up by multiplying the top and bottom by x squared. And that gives me on the top 1, and on the bottom x squared minus 2x. Right? And then here, how do we clean up this? That's a little bit tricky. You can flip over inequalities so long as you understand you have to change the direction of these. So maybe if we start with this version of it, this might be better. So that's the same as saying the absolute value of x over 2 has to be greater than 1. You know, if you remember that inequality rule, if you think about the numbers involved here, I think it should be pretty clear to you that that's true. And that means that x has to either be greater than 2 or x has to be less than -2. Right? That's a disjoint solution. A little bit of algebra 2 there. Give that some thinking. Just try some numbers and make sure that makes sense to you. And then the last part. So e to the minus x plus e to the minus 2x plus e to the minus 3x. The first term is e to the minus x, and the multiplier is, what are we multiplying here by each time? That might be a little bit tricky to figure out, but remember that when you multiply, you add exponents, so we are in fact multiplying by another e to the negative x each time. E to the negative x times e to the negative x, you add the exponents, it gives you -2x. So make sure you understand your exponent rules there. So the sum is equal to the first term, e to the minus x, over 1 minus the multiplier. All right? And if you don't like the negatives in there, you could say, you know, I'm going to multiply the top and the bottom by e to the x. And that would be, that would clean it up a little. So e to the minus x times e to the x is 1. And then here we'd have e to the x minus 1. So I think that's probably a better version of it. And then the multiplier, e to the negative x, has to be less than 1, the absolute value of this. Well, e to a power, that's only ever going to be positive, so that's the same as saying this. And then if we want to figure out what's going on here, we could take the natural log of both sides. So natural log of e to the negative x is negative x, would have to be less than 0. Natural log of 1 is 0. So that means x has to be greater than 0. Right? So that works for any x's that are less than 0. And that's what it adds up to. Those 26 and 27 really anticipate a lot of the stuff that we're going to do in this chapter. Those are the most important problems in this little section here, for sure.